Hey everyone, I wanted to introduce you to the idea of dynamic programming, which is a way that you can really speed up your code during interviews. It's not something that you want to reach for as your first tool. It's one of those things that kind of comes out in the match phase or the plan phase, and sometimes it comes out really in the review and evaluate phase. So in this problem, I'm going to show you it coming out in the review and evaluate phase to kind of show you what I mean by dynamic programming. So let's think about a problem that you've seen before. Fibonacci sequence, right? What's the Fibonacci sequence? Well, it's any number in the Fibonacci sequence is the previous two numbers from the Fibonacci sequence added together. Starts at 0, goes to 1, and so if you have 0 and 1, you can get the rest of the Fibonacci sequence from there. So let's write a function, def if I Fibonacci, Fibonacci. And what we'll do is we'll print the nth Fibonacci number. So we'll print the nth Fibonacci number. Now, if you've done Fibonacci before, often it's used to demonstrate recursion. And so you might think, I'll use recursion. So let's do that real fast. Def fib, it's going to be my internal recursive function. It'll take n. And so I'll need my base cases. If n is 0, return 0. If n is 1, we'll return 1. And so those are my base cases, and from there I can get any other number. So all I have to do is return turn fib of n minus 1 plus fib of n minus 2. And so that's the whole Fibonacci sequence. So if, I'll print fib of n here, and you can see what I mean. So we'll call Fibonacci, and we'll pass in, let's say, 1. And we get that, we get 1, great. Now let's pass in 2. We still get 1 because the second number is 1. And then if we pass in 3, we get 2. And so that's correct. Let's pass in a few larger numbers just to make sure it's working. We got 5, great. Let's do 7. Okay, 13. So it looks like our function is working, and that's fine. But now let's look at Fibonacci of 33. And as you can see, it's taking a minute. And it's a big number, but it took like a while to calculate. And your computer's pretty fast, so it's really doing a lot of operations here. Let's actually look at how many operations it's doing. I'm going to call Fibonacci rather than on 33 on 7 in Python Tutor. We'll visualize this, and what we'll get is 203 steps. Now the reason for that, if you look, when we call Fibonacci on 7, we have to call fib on 7. And then in order to get that, we have to call it on 6, and then we have to call it on 5, and 4, and 3, and 2, and 1. And so eventually we'll return 0 and 1. So this one, n minus 1, once it got down to 2, we got to 0. And then what happened was then fib of n minus 2 got called. And so then we had to get down to, we had to get down to 1, and then we had to get down to 0. And so now that this function call is collapsing and returning 2. And so then the third Fibonacci number was 2. And so now n is 2, and it's returning 1. And it turns out that for each call, we actually kind of have to calculate the whole stack again twice, right? For every number that we've got to get, you can see that it's going back down to 2 and back down to 1 and then back down to 0 and then 1. And so now we're getting 5. Okay, so the third Fibonacci number, 5. And then n is 4. And then we've got to calculate 3 and then 2 and then 1 again. So we're recalculating everything over and over again. So the thing is, Fibonacci of n, or fib of n, gets called multiple times per n. And that's the thing about this way of solving things, especially with recursion, is that you tend to call the same function over and over again, even when the result is stable. Even when you call fib of n and you know that it's going to be a specific result, like fib of 5 is always going to be whatever fib of 5 is, it's not going to change in between function calls. It's a stable result. We don't have that information to kind of refer back to. And so we have to recalculate it for sort of both sides of this tree here that we've done. And if you remember in the trees section, when we recursed over a binary tree, we had sort of the whole left side had to resolve before the right side could resolve. And it's the same idea here. So in order to make this a lot simpler, right, what we'll call is, we'll call it Fibonacci dynamic, right, of n. And what we'll do is, it's basically simpler to just do this basically with a cache, where we keep track of the numbers and hold on to them rather than recalling the function over and over again. So if we create a cache variable, and yeah. Our cache can be a dictionary, for instance, and the 0th Fibonacci number is 0, and the 1st Fibonacci number is 1. And then I can say if there's a n, or sorry, yeah, cache of n. Really, we want to use .get of n, return cache of n. Otherwise, we want to do this iteratively, right? And when we do it iteratively, we remove a huge number of steps because we don't have to kind of go back down the tree every single time. So for n in range of 2 to n plus 1, so that it actually goes all the way to n, what we'll do is if, let's see, yeah, cache of n equals cache of n minus 1 plus cache of n minus 2. That's that same calculation that we have up here, Fibonacci of n minus 1 and Fibonacci of n minus 2, but we're accessing this spot in the map. And then at the end, we can return cache of n. If we run that, that's that Fibonacci 33 here. So I'll call that same Fibonacci dynamic on 33, and we'll print it because I'm not printing here. We'll print this here. Print. And you can see first this one runs, this one up here, and then the second one runs and it's just lightning quick. I'll comment this out so you can see exactly how fast it runs. It's so much faster. And if you want to see it in Python Tutor, so you'll see here in this, we're just calling Fibonacci of 7. So I'm going to paste this in, and we're going to call it on 7. I'm going to comment, I'm going to get rid of these. You can see. So it was 203 before. This one only takes 21 steps. So that's a way for you to take the idea of recursion and translate it into a dynamic programming approach where we cache the results so that subsequent function calls to of the same variables are not necessary. Now, we don't actually need this whole cache to make this happen. So what we can do is say, I'll maintain that, like, if, whoops, I'll maintain that if Fibonacci, if n is 0, return 0. If n is 1, return 1. And then I can say a is 0 and b is 1. Because we only need two variables, really. And so we can kind of go over this whole thing again and say c equals a plus b. And then we can say a equals b and b equals c after we set c. So that way we're only holding on to the last two numbers that we saw. And at the end, instead of returning cache of n, we return c, the third variable. And so you can see this happen even faster. But if you look at how this is run, and if you skip forward to the end, you can see that there's actually a pretty big space complexity here, as in we have to store all the numbers from 0 to n in order to calculate the nth Fibonacci number. But in this example, I'll do it on 7 just to spare us. It takes 34 steps instead of like 21, which is a little bit more, but it's not going to be too much more. It's not 1/3 more steps. But the thing that's nice about it is that if you look, the space complexity never gets over 3 variables, so it's constant. It stays the same, and so it doesn't matter how high n is. What we're doing is we don't return anything, but we get our Fibonacci number just with 3 variables. So we can edit this to make it be 33. I can show you that it's 138 steps to get to 33, and that's not actually that bad. So that's the difference, and that was in the review and evaluate phase. What's key to note about this is it didn't happen. I didn't just think, dynamic programming, I'll use that to solve this problem. I thought, okay, so I understand this problem as a recursive algorithm. And so how do I take this recursive algorithm, cache the information so that I can reduce subsequent function calls that will have the same result? And that's how I discovered this dynamic programming solution. So that's kind of an intro to what dynamic programming looks like. We'll go over some more other problems in some later videos.